In this problem, we are asked to figure out the moment a force along the line AE makes with the axis defined by dB. And this is problem 3.59 from Beer Vector Mechanics for Engineers, 12th edition. Now, what we need to see that this is a 3D problem, and it was a complicated problem. There's a lot of dimensions, so I didn't want to try to recreate this problem and draw it. So that's why I've just copied it. But we need to realize it's 3D space and its moment about an axis. Because it's the moment about an axis, dB, is equal to the unit vector of dB dotted with a position vector, and that position vector is going to point, we're going to define it more accurately later, but it's going to point from somewhere on the axis that we're trying to find the moment about to our force. So this is going to be the position vector r. And then r is going to be crossed with a force, and our force is along this AE rope. Now we're going to define this force r better when we get to it, but just know it can go from any point on the axis to any point along our force. So first thing, let's define what our unit vector is, and this unit vector is going to define how this axis dB points in space. To do this, we need to define a few parts. We need to know the position of D. So D is 0 in the X, up 0.7 in the Y, 0 in the Z. So 0, 0.7, 0. In B is the other point that we know. It's 1.2 along the X, it's 0.35 along the Y, and it's 0 along the Z. So 1.2, it's 0.35, and it's 0. Now, we're free to choose whatever direction we want this to point. We can choose to have a vector that points from D to B, or we can choose to have a vector that points from B to D. I'm going to choose D to B, and this determines the way I subtract these 2 points from each other. I want to subtract the tail from the head, so I'm going to subtract point D from point B. So this position vector, dB, is going to be equal to I'm just going to write the position of B minus the position of D. So this is going to be equal to, 1.2 minus 0 is 1.2i. 0.5 minus 0.7 is minus 0.35j. And 0 minus 0 is plus 0k. Because I'm working with this form right here, the scalar triple product, I eventually want to get it to the point where I have the moment is going to equal to a matrix where my first column is my unit vector, my second column is my r vector, my position vector, and the third the third row is my force. So I really want I, j, and k components, so I want to keep all of my components together. So now that I have figured out the position vector, I can figure out the magnitude of this position vector. The magnitude of this position vector is 1.2 squared plus minus 0.35 squared. And I can go to my calculator and calculate what this is. And I get this is equal to 1.25. Okay, so I know my unit vector is equal to, the definition of the unit vector is going to be RdB over the magnitude of our dB. So this is going to be equal to 1.2 over 1.25i minus 0.35 over 1.25j plus 0 over 1.25k. And I can simplify this, and I can get what my unit vector is. So 1.2 divided by 1.25 is 0.96, and 0.35 divided by 1.25 is equal to 0.28. So I get 0.96i minus 0.28j plus 0k, and this is my unit vector. So this is some unit vector that I have. Now that I found my unit vector, I want to figure out what my position vector is. My position vector, as we said here, is it's a vector that points from this line, dB, to my force, AE. And there's some convenient points to pick. A is a pretty convenient point to pick, or E is a convenient point to pick, and D is a convenient point, and B is a convenient point. You can pick any combination of those, any that you want. I am going to choose to go from D to A. It's just what I want to choose. So I need to know what point A is. So point A, where is point A? Point A is 0 in the X. We don't go anywhere in the X direction. We go 0.2 in the Z direction. So we go 0.6 in the Y direction, 0.2 in the Z direction. So when we figure out this position vector, again, the position vector dA is going to be equal to the position vector, the point A minus point D. We subtract the tail from the head. So this is equal to 0 minus 0i, so 0i. Then we have 0.6 minus 0.7j, so minus 0.1j. And we have 0.2 minus 0k, so plus 0.2k. And that's my position vector. So the last thing I need to do in terms of setup is figure out what my force vector is. Now my force is along a line. And a force along a line is given by my force is equal to the force times the position vector over the magnitude of that position vector. All right, so I know what the force is. The magnitude of my force is 55. That's given in the problem. I need to figure out my position vectors of the force. Well, I know point A. Point A is right here. The other point I need is point E. So point E, I go 0.9 in the I. I go 0.9. Then I go up 0 in the Y. And I go 0.4 in the Z. So that's where point E is located. So this position vector is this position vector AE. It's going to be equal to E minus A. And this is going to be equal to 0.9i, 0.9 minus 0, and then minus 0.6j, and 0.4 minus 0.2 is plus 0.2k. So that is that position vector. The magnitude of this position vector is equal to the square root of the different terms here. So 0.9 squared plus minus 0.6 squared plus 0.2 squared. So let's do that. We want the square root. So this is equal to 1.1. All right, so now we know everything for this force. So my force is equal to 55 times All right. 0.9 over 1.1i minus 0.6 over 1.1j plus 0.2 over 1.1k. And let's just multiply these out. So 0.9 times 1 divided by 1.1 times 55. We get 45i. So we have 45i minus 0.6 divided by 1.1 times 55. We get minus 30j. And then 0.2 divided by 1.1 times 55 is plus 10k. So this is my force, and these are in newtons. This is in, my position vector is in meters. But what I can finally do is I can find the determinant of the matrix. So this matrix, the moment about dB is equal to, I need a matrix where my first row becomes my position vector. So this is going to be 0.96 minus 0.28 and 0. My second row becomes my position vector dE. So I have 0, I have minus 0.1, and I have 0.2. My third row becomes my force. So I have 45, I have minus 30, and I have 10. Now, what do I want to do? I want to duplicate these last two rows. So I have the first two columns, sorry. 0.96 minus 0.28. Should be still on the screen, yes. Then 0 and minus 0.1 and 45 and minus 30. Okay, now the last thing I want to do is I want to pick diagonals of 3. Any diagonal of 3 that goes this way, I'm going to add together. So in this case, I'm going to have the moment, I'm going to leave the moment out, but this is just going to be equal to 0.96 times minus 0.1 times 10. That's this diagonal. Then I'm going to have plus minus 0.28 times 0.2 times 45. That's this diagonal. And then the final diagonal is 0 times 0 plus 0, 0, and minus 30. And that might just be a little off the screen. But now we need to go the other way. So we need to say, all right, now I need to subtract off anything that's going this way. So I have, this is minus. Okay, the first one is minus 0.28 times 0 times 10. The next one is 0.96 times 0.2 times minus 30. And then the last one is 0. 0 times minus 0.1 times 45. And we're still on the screen. So now we just need to go on the calculator. And this is one equation. And we can put it in the calculator. 0.96 times minus 0.1 times 10 plus 0.28 plus minus 0.28 times 0.2 times 45 plus, so I don't need to put the next one in, it's just 0, minus the next, this term right here, well, this term is 0, so I can just get rid of it. This term is 0, and this term is 0. So I have a minus 0.96 times 0.2 times minus 30. And I get that my moment about the axis dB is going to be equal to 2.28 Newton meters. This is a positive 2.28 Newton meters. That means that my assumption of which way this unit vector pointed was correct. If it was incorrect and I had made the unit vector point from D to B, all that would happen is I'd have a negative value here. That's all that would happen. And this would be my answer as a scalar form. If I wanted to get a vector form, I would take this 2.28, I would multiply it by the unit vector, and that would give me a vectorized form.